Hello, hello, Madhav.
Hello. Hello.
Our voice is audible.
Yes, sir.
Okay, I will start.
Sure.
Thank you. Okay, today we will see standards and calibration. Therefore, basically, measurement is an act of quantitative comparison between a predefined standard and the unknown magnitude of a physical quantity. In order that the results are meaningful, the following two requirements must be met in the act of measurement. First, the standard that is used for comparison must be well established, highly accurate and reproducible. And second, the measurement devices and the calibration procedures adopted in the act of measurement must have proven reliability. Now, standards of measurement. A standard of measurement is defined as the physical representation of the unit of measurement. A unit of measurement is generally chosen with reference to an arbitrary material standard or to a natural phenomenon that includes physical and automatic constants. For example, the SI unit of mass, namely kilogram, was originally defined as the mass of a cubic decimeter of water at its temperature of maximum density, that is at 4 degrees Celsius. The material representation of this unit is the International Prototype Kilogram, which is preserved at the International Bureau of Weights and Measures at Sceaux, France. Further, prior to 1960, the unit of length was the carefully preserved platinum iridium bar at Sceaux, France. In 1960, this unit was redefined in terms of optical standards, that is in terms of the wavelength of the orange red light of Krypton 86 lamp. The standard meter is now equivalent to 1650763.73 wavelengths of Krypton 86 orange red light. Similarly, the original unit of time was the mean solar second, which was defined as 1 divided by 86,400 of a mean solar day. However, the current internationally recognized unit of universal time is based on a cesium clock. It is now defined in terms of frequency of the cesium transition to its hyperfine state, unperturbed by external fields, which occurs at 9192631770 Hz. The use of cesium clock gives an accuracy exceeding 1 microseconds per day. Therefore, it is considered as the primary time and the frequency standard. In fact, a number of standards have been developed for other units of measurements, including standards for fundamental as well as derived quantities, which may include mechanical, electrical, thermal, optical, etc. There are different types of standards of measurement. They can be classified according to their function and type of application. They are briefly described as follows. First is international standards. International standards are devices designed and constructed to the specifications of an international forum. They represent the units of measurement of various physical quantities to the highest possible accuracy that is attainable by the use of advanced techniques of production and measurement technology. These standards are maintained by the International Bureau of Weights and Measures at Sceaux, France. For example, the International Prototype Kilogram, Wavelength, Krypton 86 orange red lamp, and cesium clock are the international standards for mass, length, and time, respectively. However, these standards are not available to an ordinary user for purposes of day-to-day comparisons and calibrations. Next is primary standards. Primary standards are devices maintained by standards organizations, national laboratories in different parts of the world. These devices represent the fundamental and derived quantities and are calibrated independently by absolute measurements. One of the main functions of maintaining primary standards is to calibrate or check and certify secondary reference standards like international standards. These standards also are not easily available to an ordinary user of instruments for verification or calibration of working standards. Secondary standards are basic reference standards employed by industrial measurement laboratories. These are maintained by the concerned laboratories. One of the important functions of an industrial laboratory is the maintenance and periodic calibration of secondary standards against primary standards of the National Standards Laboratory Organization. In addition, secondary standards are freely available to the ordinary user of instruments for checking and calibration of working standards. Now, working standards, these are high accuracy devices that are commercially available and are duly checked and certified against either the primary or secondary standards. For example, the most widely used industrial working standard of length are the precision gauge blocks made of steel. These gauge blocks have two plane parallel surfaces, a specified distance apart with accuracy tolerance in the 0.25 to 0.5 micron range. 1 micron is equal to 10 raised to minus 6 meter. Similarly, a standard cell and a standard resistor are the working standards of voltage and resistance respectively. Working standards are very widely used for calibrating general laboratory instruments, for carrying out commercial measurement, or for checking the quality of industrial products. Next is calibration. Calibration is the act or result of quantitative comparison between a known standard and the output of the measuring system, measuring the same quantity. In a way, the process of calibration is in effect the procedure for determining the scale of the measuring system. If the output-input response of the system is linear, then a single point calibration is sufficient, wherein only a single known standard value of the input is employed. However, if the system response is non-linear, then a set of known standard inputs to the measuring system are employed for calibrating the corresponding outputs of the system. The process of calibration involves the estimation of uncertainty between the values indicated by the measuring instrument and the true value of the input. In fact, calibration procedure is the process of checking the inferior instrument against a superior instrument of known traceability, certified by a reputed standards organization or national laboratory. Herein, the term traceability of a calibrating device refers to its certified accuracy when compared with superior standard of highest possible accuracy. Calibration procedures can be classified as follows. Primary calibration. When a device or system is calibrated against primary standards, the procedure is termed as primary calibration. After primary calibration, the device is employed as a secondary calibration device. The standard resistor or standard cell available commercially are examples of primary calibration. Secondary calibration. When a secondary calibration device is used for further calibrating another device of lesser accuracy, then the procedure is termed as secondary calibration. Secondary calibration devices are very widely used in general laboratory practice as well as in the industry because they are practical calibration sources. For example, standard cell may be used for calibrating a voltmeter or an ammeter with suitable circuitry. Direct calibration with known input source. Direct calibration with a known input source is in general of the same order of accuracy as primary calibration. Therefore, devices that are calibrated directly are also used as secondary calibration devices. For example, a flow meter such as turbine flow meter may be directly calibrated by using the primary measurements such as weighing a certain amount of water in a tank and recording the time taken for this quantity of water to flow through the meter. Subsequently, this flow meter may be used for secondary calibration of other flow metering devices such as an orifice meter or venturi meter. Next is indirect calibration. Indirect calibration is used based on the equivalence of two different devices that can be employed for measuring certain physical quantity. This can be illustrated by a suitable example, say a turbine flow meter. The requirement of dynamic similarity between two geometrically similar flow meters is obtained through the maintenance of equal Reynolds number, that is rho 1 V1 D1 divided by mu1 is equal to rho 2 V2 D2 upon mu2. Voice is audible or not? Hello, Madhav. Hello.
Yes, audible.
Then the Kailash sir is saying he not audible.
No, it is
Kailash
audible.
sir. Huh? Please check.
It,
Okay. For such a condition, the discharge coefficients of the two meters are directly comparable. Therefore, it is possible to carry out indirect calibration, that is to predict the performance of one meter on the basis of an experimental study of another. This way, a small meter may be employed to determine the discharge coefficient of large meters. Also, the discharge coefficient of the meter intended for gas may be determined by carrying out
बोला काय झालं
इसकट ते पाजर आ
Okay. Now next is routine calibration. Routine calibration is the procedure of periodically checking the accuracy and proper functioning of an instrument with standards that are known to be accurately reproducible. The entire procedure is normally laid down for making various adjustments, checking the scale reading, etc., which conforms to the accepted norms or standards. The following are some of the usual steps taken in the calibration procedure. First, visual inspection of the instrument for the obvious physical defects. Second, checking the instrument for proper installation in accordance with the manufacturer's specifications. Third, zero setting of all the indicators. Fourth, leveling of the devices which require this precaution. Fifth, recommended operational tests to detect major defects. Sixth, the instrument should preferably be calibrated in the ascending as well as descending order of the input values to ensure that errors due to friction or stiction are accounted for. Next, the calibration device should have superior level of traceability of standards as compared to the calibrated device. Therefore, this is the end of the first chapter. Now we will start second chapter. Okay. Now we will start chapter 2. Static characteristics of the instruments. Therefore, in this chapter, we will study different characteristics of the instruments. First is the accuracy. Accuracy of a measuring system is defined as the closeness of the instrument output to the true value of the measured quantity as per standards. However, in usual practice, it is specified as the percentage deviation or inaccuracy of the measurement from the true value. For example, if a chemical balance reads 1 gram with an error of 10 minus 2 gram, the accuracy of the measurement would be specified as 1%. Accuracy of the instrument mainly depends on the inherent limitations of the instrument as well as on the shortcomings in the measurement process. In fact, these are the major parameters that are responsible for systematic or cumulative errors. In other words, the accuracy of an instrument depends on the various systematic errors involved in the measurement process. For example, the accuracy of a common laboratory micrometer depends on instrument errors like zero error, errors in the pitch screw, anvil shape, etc. And in the measurement process, errors are caused due to temperature variation effect, applied torque, etc. Therefore, the accuracy of the instruments can be specified in either of the following forms. Percentage of true value is equal to measured value minus true value into 100 divided by true value. Percentage of full scale deflection is equal to measured value minus true value into 100 divided by maximum scale value. It may be noted that accuracy specification of an instrument as a percentage of full scale deflection is less accurate than the percentage of true value. For example, an error plus minus 1% of full scale deflection of a voltmeter having a range of 1000 volt means that a true voltage of 100 volt could be read from 90 to 110 volt. However, as a percentage of true value, it would read from 99 to 101 volt. Next is precision. Precision is defined as the ability of the instrument to reproduce a certain set of readings within a given accuracy. For example, if a particular transducer is subjected to an accurately known input and if the repeated readouts of the instrument lie within say plus minus 1%, then the precision or alternatively the precision error of the instrument would be stated as plus minus 1%. Thus, a highly precise instrument is one that gives the same output information for a given input information when the reading is repeated a large number of times. Therefore, this is nothing but precision. Therefore, there is a difference between accuracy and precision. See that in the first, our target is nothing but this bull eye. Now, if all the bullets are fired around the periphery or at one point around on the periphery of the circle, then we can say that high precision with poor accuracy, because precision means what? Repeatability. If you will say now this figure number B, good average accuracy with poor precision. Whatever these bullets are shot near to the bullseye, and but all the bullets are shot, they are scattered. Therefore, you can say that good average accuracy with poor precision. Now here all the bullets, whatever 9 bullets are, they are shot at the bullseye. Therefore, this is high accuracy with high precision, and this deep part, poor accuracy with poor precision, because all the bullets are scattered and they are not shot at the bullseye. Therefore, this is poor accuracy with poor precision. Now next is resolution or discrimination. It is defined as the smallest increment in the measured value that can be detected with certainty by the instrument. In other words, it is the degree of fineness with which a measurement can be made. The least count of any instrument is taken as the resolution of the instrument. For example, a ruler with a least count of 1 mm may be used to measure to the nearest 0.5 mm by interpolation. Therefore, its resolution is considered as 0.5 mm. A high resolution instrument is one that can detect smallest possible variation in the input. Next is threshold. It is particular case of resolution. It is defined as the minimum value of input below which no output can be detected. It is instructive to note that resolution refers to the smallest measurable input above the zero value. Both threshold and resolution can either be specified as absolute quantities in terms of input units or as percentage of full scale deflection. Both threshold and resolution are not zero because of various factors like friction between moving parts, play or looseness in joints, more correctly termed as backlash, inertia of the moving parts, length of the scale, spacing of graduations, size of the pointer, parallax effect, etc. Next definition is static sensitivity. Static sensitivity, also termed as scale factor or gain of the instrument, is determined from the results of static calibration. This static characteristic is defined as the ratio of the magnitude of response to the magnitude of the quantity being measured. That is, static sensitivity K is equal to change of output signal divided by change of input signal. In other words, sensitivity is represented by the slope of the input output curve if the ordinates are represented in actual units. With a linear calibration curve, the sensitivity is constant. However, if the relationship between the input and output is not linear, the sensitivity varies with the input value and defined as shown in figure 2.2b. Therefore, this is 2.2b static sensitivity. This is linear graph. Therefore, you can take only one graph, that is one triangle where maximum points you can accommodate. You can find out that slope K is equal to delta Q naught divided by delta Qi. In another graph, this is non-linear graph curve. Therefore, you can take at least two triangles and you can find out slope of that two triangles Ka and Kb. The sensitivity of a typical linear spring whose extension is directly proportional to the applied force can be defined as, say, 450 Newton per mm. Similarly, the sensitivity of a non-linear type of copper constant and thermocouple is found to be maximum at 350 degrees Celsius and is 60 microvolt per degree Celsius. It may be noted that in certain applications, the reciprocal of the sensitivity is commonly used. This is termed the inverse sensitivity or the deflection factor. Next is linearity. A linear indicating scale is one of the most desirable features of any instrument. Therefore, manufacturers of instruments always attempt to design their instruments so that the output is a linear function of the input. However, linearity is never completely achieved and the deviations from the ideal are termed as linearity error. In commercial instruments, the maximum departure from linearity is often specified in one of the following ways. First is independent of the input. If the deviations of the output of the instrument from the best fitting straight line drawn through the calibration points does not vary with the input, then non-linearity is specified in terms of higher value of the maximum deviation that occurs on the positive and negative sides of the best fitting or idealized straight line. This value is usually expressed as plus minus percentage of full scale deflection. Next is proportional to input. If the deviations of the output of the instrument from the idealized straight line vary with the input, then non-linearity is specified as a function of the input. In such cases, the maximum deviation points on the positive and negative sides of the idealized state line are joined with the origin and their slopes are determined. The higher value of the percentage change in slope with respect to the idealized line is usually expressed as plus minus percentage of non-linearity with respect to the magnitude of input values. Combined independent and proportional to the input. In certain cases, the deviations of the output may not vary with the input for a part of the range and may show proportional variation for the rest of the range. In figure 2.3c, a typical calibration curve shows an independent deviation at the lower range and proportional variations at the higher range with respect to the idealized state line. In this case, the maximum deviations at the lower range is taken care of by specifying say plus minus y% of full scale deflection and by say plus minus x% of the input value. Therefore, these are the graphs for typical specifications of non-linearity. However, it may be noted that in actual practice, the non-linearity of a complex type of calibration curve is obtained as say plus minus y% of full scale deflection and also as plus minus x% of full scale input value. The non-linearity of the instrument is then stated as plus minus y% of full scale or plus minus x% of the input, whichever is greater. Further, it may be instructive to note that in commercial practice, the term linearity is commonly employed in place of non-linearity. For example, the statement linearity is equal to plus minus 2% of input means non-linearity is equal to plus minus 2% of input. In most commercial instruments, linearity is generally implied. In such cases, linearity specifications are equivalent to accuracy specifications and either of them may be specified. However, in instruments that have non-linear characteristics, the readout scale of the instrument is not uniform and is calibrated accordingly. Next is range and span. The range of the instrument is specified by the lower and upper limits in which it is designed to operate for measuring, indicating, or recording the measured variable. The algebraic difference between the upper and lower range values is termed as the span of the instrument. The range of the instrument can be either unidirectional, that is 0 to 100 degrees Celsius, or bidirectional, for example, minus 10 to 100 degrees Celsius, or it can be expanded type, for example, 80 to 100 degrees Celsius, or 0 suppressed, for example, 5 to 40 degrees Celsius. The overrange or overload capacity of the instrument is the maximum value of the measurand that can be applied to the instrument without causing a perceptible change in its operating characteristics. Further, the recovery time of the instrument is the amount of time elapsed after the removal of the overload conditions before it performs again within the specified tolerances. Next is hysteresis. It is defined as the magnitude of error caused in the output for a given value of input when the value is approached from opposite directions, that is from ascending order and then descending order. This is caused by backlash, elastic deformations, magnetic characteristics, but is mainly due to frictional effects. Next is deadband. It is defined as the largest change of the measurand to which instrument does not respond. Next is backlash. It is defined as the maximum distance or angle through which any part of the mechanical system may be moved in one direction without causing motion of the next part. Next is drift. It is defined as the variation of output for a given input caused due to change in the sensitivity of the instrument due to certain interfering inputs like temperature changes, component instabilities, etc. Therefore, how to select the instrument? Therefore, the various considerations involved in the selection of the instrument include following from the value viewpoint. That is instruments qualities value guided. First, accuracy and precision characteristics, including other specifications like sensitivity, linearity, hysteresis, zero, and sensitivity, drift, deadband, etc. Second, nature and type of data available, that is whether analog, digital, continuous, or sampled. Third, nature and type of readout, that is whether indicating or recording type, etc. Fourth, nature of further data computations if required. Fifth, signal to noise characteristics of the transducer and the system fidelity, especially when extensive data transmission or translation is involved. Sixth, dynamic response characteristics if input signal is time dependent. Seventh, susceptibility to environmental disturbances. Next is convenience aspects. First, suitability for the given application, that is whether for laboratory use, field use, or both. Adaptability to different sizes of inputs, that is scale expansion, range changes, etc. Ease in calibration when needed, simplicity and ease of instrument behavior diagnosis, material durability, non-fouling design, foolproof assembly, maintenance repair, local representation and all steady delivery, safety in use, ready self indication or check determination, or in case of instrument malfunction. Therefore, this is nothing but next is cost and cumulative initial cost of the instrument procurement, installation, including the various attachments and accessories. Second, maintenance, repair and recalibration, etc. Third, running cost. Fourth, expected lifespan considering the salvage value of components which may be used in other similar instruments as interchangeable modules. It is worth mentioning here that the establishment of true costs and values of an instrument is an ideal which is usually and understandably approached rather than attained. In practice, it is found that a number of instruments may be marketed by different commercial firms for a particular measurement. Therefore, the normal procedure of selecting particular instrument consists of carefully studying the positive and negative points of each instrument, including the prevailing market price and the availability. This, combined with mature judgment, intuition, and experience, helps to arrive at the value-guided optimal selection of the instrument for the given application. Okay, thank you very much. Now we will stop here. Next lecture that Gidde sir will engage.